Okay, so with this, I will then switch to the next part given by the PhD researcher in my group, Jiali, to talk about the outline of a paper we recently generated on the topic of deep learning accelerated gold nanocluster synthesis. And this is the overall structure, and you will be able to find our full paper on the preprint archive list, together with all the code and all the data available there. With this, I will just give the stage to Jiali and talk about how we use these methods for this example.
Thanks for Dr. Xiaonan's introduction about the deep learning method. Now I will introduce you how to apply machine learning method to create better gold nanoclusters. And as you can see that gold in bulk is quite boring. It doesn't have any fascinating properties. You enlarge it or make it smaller, it doesn't make any difference. However, when we lower down the scale size of gold to nanoscale, like less than 2 nanometers, it can have very fascinating properties such as very strong photoluminescence. As you can see in the tube, each tube contains one specific atomic precise gold nanoclusters with a specific molecular formula. And the only difference between them may only be one difference in gold atoms. And as you can think that if we can use this kind of fascinating nanoparticles in manufacturing process, we can give either cars very nice colors and so on. But the difficulty is that this kind of process, this kind of synthesis process is quite complex. And what we want is we want to synthesize the gold nanocluster at atomically precise with defined molecular formula. And however, nowadays, it is due to the complexity of the process, and there are many variables, we are very hard to control the whole synthesis process. The scientists don't know what's the right recipe until they have done the experiments. But machine learning tool can give us some idea of how to make this whole synthesis process more controllable or more predictable. And I will first introduce you about our best performed model. And as we said about, it is a combined neural network approach. We first have a graph convolutional neural network, which I will refer to as GCNN. And this neural network is based on the concept of convolutional neural network. We will be able to input the molecular graph into this neural network, and it will calculate the information of the atom, and the atoms surrounded it, and the bound information surrounded of it, to output some fingerprint information of the molecule, which contains both the structure information and some of the physicochemical information. And to do the classification task, we implement a one-shot learning method, the Siamese neural network. As you can see, you first have an input 1. The input 1, we may already know the class of the input 1. It can be successful synthesis of atomic precise gold nanocluster, which we label as 1. And if we have another input 2, it doesn't have any labels, but it contains all the information of key reaction components such as the ligand, the solvent, reducing agent, and gold precursors, and as well as the reaction conditions. And they will be both input into a sister neural network. The sister neural network will share the sandwich between each other. And after that, the output will be adjust to some loss function. Then it will decide whether input 1 and input 2 are in the same class or not. And by doing this, we have developed a deep learning framework. And for the left part will be the classification task, classification model. And as you can recap, our best model is GCNN plus SNN models. And this one, we first have a very limited number of examples, 54 in our case. And then we input that into the GCNN plus SNN models. The GCNN is to give the information, and SNN is to do the classification task. By training this, we are able to generate a large number of new examples by inputting different reaction conditions or different key reaction components combinations. Then we can get the probability of each recipes so that we can choose the recipe with highest probability to carry out the experiments. And for the interpretability part, we always want to know more things about the model. We want to gain the chemical insights, not just to get out the numbers. So we take the well-trained GCNN plus SNN models, and with a randomly generated large number of different conditions, we are able to generate a large number of labeled data. Then we can train a decision tree. The decision tree cannot be trained by 54 examples, but if we generate a large number of labeled data, we are able to do that. The decision tree is aimed to rank all the features, the important factors, in a sequence of importance, so that we can know which kind of factors may be quite important in these complex chemical reactions. And to describe either the molecular information and condition informations, we have find 17 basic descriptors. And to describe for the explorative process, which we define as we change the key reaction components combinations, we choose these are the ligand, solvent, and reducing agent, because the gold precursor never change. People always use this one. And for the reaction synthetic conditions, we take the reactant concentration, the pH, and the reducing reaction temperatures as very important descriptors. And we combine them together to form what we call basic descriptor set. After that, let me introduce you about our model detail. This is a simplified version of our model detail. First, we need to get the data input into the neural network. The data is converted by a package called RDKit. I will introduce you about this later. And then after the data is input into the GCNN, we are able to construct the fingerprint for the molecules. And after the fingerprint has been constructed, we combine them together with the basic descriptors I introduced you before to input into the SNN. And after that, the SNN will do the classification task, and then we can get the output of whether it is successful or not, 1 or 0. Actually, it has some probability. And this is a more detailed version of our model. As you can see from the left, this is a GCNN neural network. We input the molecular graph inside, which will be a graph tensor converted by RDKit. Then after the GCNN neural network, the fingerprint of the molecule can be calculated. We have done this for all 3 key reaction components, the solvent, ligand, and reducing agent. We combine them together with the basic descriptor sets to form the intermediate input vectors. And this will be the input into our CMS neural network. Then the classification task can be done. And to assess the performance, we have assessed it from 2 aspects. The first aspect is about the explorative process, and the second one will be the synthetic condition optimization process. Firstly, let me prove that the structure information of the molecules has been learned by the GCNN. We do this by calculating the Euclidean distance of different ligands. And the Euclidean distance of 2 vectors is like vector A and B. The distance will be D here. And because we output a fingerprint vector, so each ligand has a finger vector to describe it. And for the 3 Thailand molecules belong to the same group of molecules, they have quite small Euclidean distance between each other. And for another group of molecule, such as a gluten cyan, it has quite large distance between the others. So it proves that the structure information has been learned by our GCNN neural network. And for the statistic part, please look at this red bucket. It is a MCC. MCC is an indicator to compare the predictability of our model to a random guess. If MCC is equal to 0, it means it is the same as a random guess, but it is more than 0, it means it's better. And the maximum number of MCC will be 1. Please note that we didn't just do the test for our GCN plus SN models. We have changed the classification models to test for dense neural network, support vector machines. And we have found that, as you can notice, as long as we stack the GCNN with the classification model, you can get quite good MCC number out. However, this is due to the heterogeneous nature of our data set. We get our data set mainly has composed of different key reaction components combinations. And to do well in the data sets, to gain good MCC, we need to be performed well in explorative process. However, it is not enough to show the ability of our data to do the synthetic condition optimization process. So we do the visualization of it. To do the visualization, please first look at the 2D heat map. The heat map is a map to plot the probability of successfully synthesis of gold nanocluster at atomic precise against pH and temperature. And you can see there is a variation of color. And as temperature increases, it predicts that the probability of successful synthesis will be lower, and it will eventually go to 0 after some temperature. It's 50 degrees Celsius here. It is actually matches well to our chemists, to the material scientists' understanding. As the temperature increases, the gold nanocluster may dissociate at a certain temperature. And we do the 5-dimensional graph visualization is to show that as long as we input the ligand concentration, the gold precursor concentration, and the reducing agent concentration also takes them into account. With each point is a 2D heat map as this. You can see the heat map will change. It means the whole process will be affected not only by 2 factors, but also by a large amount of factors. There are more factors to affect it, but 5-dimensional is the highest dimension. I can give you a good visualization. And after this shows that this whole process is actually quite difficult for human to do the predict process, but machine can actually do it. And this is for other models, for the DNN and SVM. You see there is no color change, color variation at all. It means no information has been learned by all these different classification models rather than SNN. And to validate our model capability, we have done the experimental validations. We're aiming to produce gold nanoclusters with 18 gold atoms with atomic precise. And we use our GCN plus SN model to predict the best recipe with the highest probability to synthesize such atomic precise gold nanoclusters. And we are able to synthesize it with the proven of the UV spectrum for the gold 18 nanoclusters. And to gain some interpretations, we have done the decision tree as I mentioned before. And the decision tree has done for the gold 25 nanoclusters. And it shows that the ligand to gold ratio will be a quite important factor here. And this quite matches the understanding from the community that if we want to synthesize a small gold nanocluster, like the gold 25 nanoclusters, it is quite important we have the ligand to gold ratio to be lower than a certain number. And you can see that reducing agent concentration and temperature pH are also marked as very important factors inside these complex reaction systems. To conclude, we have been able to show that machine learning method can actually accelerate the synthesis of new materials with incorporating all parameters into considerations rather than just focusing on 1 or 2 parameters nowadays. And we are able to find some quantitative probability patterns, not just qualitative relationships, especially to very complex reaction systems. You don't get any simulation model yet. And we have experimentally validated that we can successfully synthesize atomic precise gold nanoclusters. And this two-step machine learning framework can gain some insights from this kind of complex reaction systems. And we show that even with limited number of successful examples, machine learning tools can be quite powerful. And let's go to the code demonstration part. To do a good data analysis task, you first need to prepare the data quite nice. So if you look into the data folders I give you, if you open the data folder you can find the Excel called Gold Data Loader. You can open it and you can see four important worksheets. You can see the four important worksheets. The first one will be called DF. It contains all the data. And the feature C, it contains only the features. Feature D, it contains only the naming systems for key reaction components. And the labels contains all the labels, either 1 or 0, successful or not. And for the hands-on session, please put the presentation.py, this script, into your Python. Open your Spider.
Of the code.
We use this IDE because if you get very complex, you want to do a research project, and the research project is not that simple. It's better you go some IDE. And some packages are only built on certain IDEs. You cannot use it on the Jupyter Notebook, and it's not clear, and you will get messed up eventually. And please pay attention to your environment. You must be in the workshop environment. Otherwise, you cannot open the packages because the packages is installed in that environment. In the folder you download for the Gold Nanocluster synthesis, it contains many scripts. And this is the one script we create for you for the presentation. It will run all the scripts inside that folders. So please do not delete any folders or change any folders location. Okay. And if you have done that, you just click the run. You just click the run, and it will take several minutes to run because the whole neural network is quite deep. Although we only have 54 examples, but it takes a really long time to run. And I will introduce you our logics. I will introduce you about our logics in how to form the codes. And these logics can not only be applied to our research studies, but also apply to all of your works. Firstly, above all, you must need to be able to get the data, take the data into the codes to the neural networks. And this is also the script is in your folder. It's called feature label setup. You can find these parts. But actually, you can learn deep into it later after the session. You get many codes, actually, thousands of lines. And if you can recap the model detail I tell you, these are still inside the data input part. For the data input, another part is to make the simplified molecular input line entry system, the SMILES, convert into something the convolutional neural network can read. So we need to convert it into a graph tensor. And it is done by a package called RDKit, which is a very famous package for chemistry use. And after that, we will move to the fingerprint construction parts. The fingerprint construction parts, we will use the GCNN. The GCNN is inside the SNN setup script. And you can find the lines, and this part is taken to the graph tensor into the graph convolutional neural network, then calculate it out to gain the fingerprints of different molecules. After this has been done, as I as I introduced before, we need to construct the intermediate input vector, the IIV, to combine all the fingerprints with the basic descriptors, and then we can input it into the SNN here. They are also in the same script, the SNN setup. And after you have inputted in, it will do the classification task. After all of this, if you train the model, if you have already run it, you can actually see the output. The output is inside the kfold.cv. You can, it's a running script of above all. And it contains all the hyperparameters, everything you want to tune off, and it contains where to get the packages, and so on. And if you have successfully run your codes, then you will find an Excel sheet in your folder, in the Gold Nanocluster folder, or if you, in the Gold Nanocluster folders. And if you open the Excel sheet, you can find the output of the neural networks. The output you can see, first, if you see the class is a true label of different reaction conditions. And the predictive class is the output from our codes. Thank you very much. I think that's all for my presentation. And if you haven't done the coding running yet, maybe it takes some time to figure it out.